Okay, hello everyone. So this is the last slide I have presented. No? So we now move on with our next topic called numerical integration. No? So in this chapter, it deals with the definite integral of an approximating function over a particular range between the lower limit and the higher limit using the trapezoidal rule or the Simpson's rule. Upon applying the forward Gregory-Newton interpolation formula in determining the approximating function. No? Alright, so in other words, in this chapter, we're going to talk about the trapezoidal rule and the Simpson's rule. Okay, so the two will be employed, no, so that we can able to solve for the integral, no, of an approximating function. Okay, upon applying the forward Gregory-Newton interpolation formula. Okay, so objectives are as follows. Solve the definite integral of an approximating function over a particular range between the lower limit and the higher limit using the trapezoidal rule. Second, solve the definite integral of an approximating function over a particular range between the lower limit and the higher limit using Simpson's rule. Now, so those are the two objectives. Okay. So when you have your integral calculus 2, no? So you have studied different kinds of integration techniques, no? How to integrate, no? So like the integration by parts, like the using the power formula and so forth, no? So this time we have trapezoidal rule and Simpson's rule. These are integration techniques also, no? Related to numerical methods, no? Okay. So let's study each one, no? So we first start with trapezoidal rule. Consider the graph below. So here's the graph. So this is the approximating function. The line, the red line is the approximating function. Y equals f of x is the actual function, no? So we use linear interpolation here. That's why we have a line. And as you notice, we have it is we start with x sub 0 and ending up with x sub 1. Okay, and what have you noticed? The shape is a trapezoid, right? So there's a shaded area here. There's a shaded area here. Okay, so this shaded area is a trapezoid. So what is a trapezoid? So what is a trapezoid? A trapezoid is a quadrilateral wherein two sides are parallel. Okay? So one pair of opposite sides of a quadrilateral is parallel. Okay? So in this case, we have the parallel sides, no? So we have this side, okay, and this side. Okay, they are parallel. Okay, and the two remaining sides which are opposite are not parallel. So this therefore this is a trapezoid, no? So this is a trapezoid. That's why we are to study trapezoidal rule. it has something to do with our topic. Uh, so this trapezoid has something to do with our topic. So the area of the trapezoid, okay, approximates the area of the actual function under the curve. No, the area under the curve of the actual function is approximated by the area of the trapezoid. So in this case, we're going to solve some problems in solving for the area under the curve that is approximated using trapezoidal rule. So in other words, we form a trapezoid. Okay, so we form a line, so connecting the 2 points. So this is x sub 0, y sub 0. This is x sub 1, y sub 1. Okay, so connecting a line to it, connecting to line from point x sub 0, y sub 0 to x sub 1, y sub 1. Okay, and the area now below this line is the approximating area, or should I say is the approximated area of the actual function, no, which is below the graph of the actual function. Okay, in this case, the graph of the approximating function, which is a line, intersects the graph of the actual function. Okay, so this is the graph of the approximating function, which is the red line intersecting the graph of the actual function y equals f of x at points x sub 0, y sub 0, and x sub 1, y sub 1. Okay, so this is x sub 0, y sub 0, this is x sub 1, y sub 1. The graph, the area below the graph of the actual function is approximated by the area below the graph of the approximating linear function. No? So the area below the graph of the actual function is approximated by the area below the graph of the approximating linear function. Okay, so we are now to determine the formula for approximating the area below the graph of the actual function using trapezoidal rule. So in this case, the area below the approximating function is a trapezoidal area. So this trapezoid. So we have this trapezoid. So this is a trapezoidal area and can be obtained by the formula A equals 1 half h f sub 0 plus f sub 1. Okay, so this is the area of a trapezoid. No? So the area of a trapezoid, as you have learned before, let's say we have this trapezoid. And how do we find the area of this trapezoid? So the area of the trapezoid can be obtained, no, using the formula. So if this is, so this is the base and this is the altitude, no. Okay, so this is the altitude. Okay, so the base and the altitude. So that is 1 half. So we have two bases, base number 1 and base number 2. Then the height or the altitude. So the two bases are parallel, take note. So 1 half of the sum of the bases, b1 and b2, multiplied by the altitude or the height. Okay, so that's the formula. That's why this becomes 1 half h b1 plus b2. That's the area of the trapezoid. No? So in this case, in this illustration, we have b1 and b2, which are two sides that are parallel, and that is f sub 0 and f sub 1 in our illustration. So this becomes now f sub 0, f sub 1. This becomes now f sub 0 and f sub 1. b1 and b2 becomes f sub 0 and f sub 1. Okay? And the height or the altitude of the trapezoid is simply x sub 1 minus x sub 0. No? So x sub 1, okay, so this is x sub 1 minus x sub 0. No? So this is x sub 0. X sub 1 minus x sub 0, we get this altitude. No? Alright, so we now proceed. So considering the graph below for several trapezoidal area in approximating the area below the graph of the actual function, considering more than 2 points on the curve, okay, so as you notice here, we have the graph of the actual function. So there are several trapezoidal area. So we considered more than 2 points on the curve. So we have the first point, x sub 0, f sub 0, x sub 1, second point, x sub 1, f sub 1, x sub 2, f sub 2, x sub 3, f sub 3, x sub 4, f sub 4. No? So we have, in this example, we have 5 points. Okay? So we have 5 points. And in this case, the total approximated area of the actual function by trapezoidal rule is given by the formula. So this is the formula. We integrate x sub 0, we integrate the function from x sub 0 to x sub n. Okay, so in this case, this is x sub n, which is x sub 4. Okay, so it is approximated using the trapezoidal rule formula. No? So this area, so this is the actual area below the graph, no, of this function y equals f of x. It is approximated by trapezoidal rule formula. No? It is approximated by trapezoidal rule formula. So between x sub 0 and x sub 4, okay, so we have 4 trapezoids. No? First trapezoid, trapezoid 1, trapezoid 2, trapezoid 3, trapezoid 4. So the area, no, so the area below the actual function, okay, um, is becomes more accurate, no, when we have several trapezoids between 2 points, x sub 0 and x sub 4. So if we consider only one trapezoid, okay, if we consider only one trapezoid, so if this is the actual function, if we only consider one trapezoid, so the approximation is not that accurate. So this part is lost, no? This part is lost. Okay? Okay, so unlike if we form several trapezoids, so if we form several trapezoids, okay, so let's say we have those. Okay. So we have first trapezoid, second trapezoid, third trapezoid, fourth trapezoid, fifth trapezoid. So the approximation is more accurate. no? Okay, so it is very near to the actual value of the area, no? It's very near to the actual area. Okay, so that's the advantage of having several trapezoids between 2 points, no, on the graph. So let us continue. So we have here the trapezoidal rule formula. Okay, so a sub t is equals to h multiplied by 1 half f sub 0 plus f sub 1. Okay, 1 half f sub 0 plus f sub 1 plus f sub 2 and so forth, and then plus fn sub n minus 1 plus 1 half f sub n. Okay, so that's the formula, no? So such that h is equals to x sub I plus 1 minus x sub I. Okay, so we have 4h here. Okay, we have 4h. Okay, so 4 altitudes and they are all equal. Okay, all right, so also in finding the value of h, there's an alternative way on how to find h, no? So to determine h, so we have x sub n minus x sub 0 all over n. So in this case, we have x sub 4 minus x sub 0 over 4, right? So that's the formula. Alright, so that is now h. Okay? So here's a problem. So find the approximate value of the integral of square root of 1 plus x cubed dx over the range from 0 to 2, taking n equals to 4 considering the trapezoidal rule. Okay, take note of the following. So we have this is a and this is b, and this is x sub 0 and this is x sub n. Okay, x sub n. And n is 4, okay. F of x is square root of 1 plus x cubed. So this is f of x. So we have the integral of f of x dx, okay, from a to b, right? Okay, so that's the integral. And then we can replace x by x sub I. F of x sub I equals to f sub I equals to square root of 1 plus x sub I cubed. Okay, or you can use also k, f sub k square root of 1 plus x sub k cubed. Okay, now in finding for the v, use the formula for h. Okay, x sub n minus x sub 0 over n. Okay, so in that case, that is 2 minus 0 all over 4. So if we analyze the previous slide, so this is h, right? This is h. So we have 4h. So we have x sub 4 is equals to x sub 0 plus plus h plus h plus h plus h plus 4h, right? But n is equals to 4. Therefore, x sub n equals to x sub 0 plus nh. That's why n is equals to x sub n minus x sub 0 over h. That's why we get this. No, no, no. We're solving for h. We solve h and then this is n. Okay? That's why we get this. Alright? So we continue. So we have, so this is x sub 0, which is, and this is x sub 4, okay, which is equals to 2. And we get 0 0.5, no? We get 0 0.5. So therefore, the integral of the function f of x dx over a particular range, no, from a to b, so is equals to the integral of the function dx, okay, from x sub 0 to x sub n. Is approximated by a sub t, which is the trapezoidal rule formula, okay, that is equals to h 1/2 fo and so forth, no? So for n equals to 4, so n is 4, then we have integral from x sub 0 to x sub 4, no? We replace n by 4. So if we replace n by 4, this will become f sub 3, f sub 4. Okay? Alright, so we proceed now. And then we have now hi, x sub I, f sub I. So we'll construct a table. So we have each value is 0 0.5, okay, as computed, no? Then I value 0, 1, 2, 3, 4. So we start with 0, followed by 1, 2, 3, and 4. Okay? So because we have n is equals to 4. If we have n equals to 4, I starts with 0. Okay? I starts with 0 and will end up with 4. No? So this is n equals to 4. So this is now n is equals to 4. So we have x sub I. Initially, we have, so that is x sub 0. So that is x sub 0 is 0, right? Then we add h, x sub 0 plus h, we get x sub 1. So this is x sub 1, which is 0 0.5. Okay? So this is x sub 1. And then we have 0 0.5 plus 0 0.5, we get 1. This is now x sub 2. So 1 is equals to x sub 2. Then 1 plus 1.5, 1.5. Sorry, 1 plus 0 0.5, 1.5. So that is now x sub 3. Then 1.5 plus 0.5, that is 2. No? So we get 2. Okay? Then for the function values, so this is 1. So we have square root of 1 plus 0 cube. So this is f sub I, so that is f sub 0 equals 1 plus 0 cube. So we replace this by 0, we have 1. Then we replace x sub I by 0 0.5, 1 plus 0 0.5 cube, we get 1.0607, then 1.4142, 2.0917, then 3. So 1 plus 2 cube, that is 1 plus 8. 1 plus 8 is 9. Square root of 9 is 3. So we get 3. Okay? Alright, so we continue. So the integral now of this function, okay, is approximately equal to, so we substitute 0 0.5 for age. So f sub 0 is 1, then f sub 1 is 1.0607, 1.0607. So these are obtained from the table, right? So we have f sub 0, f sub 1, f sub 2, f sub 3, f sub 4. So there we have it. So then we will have an answer of 3.2833. So this is the approximated integral of square root of 1 plus x cubed dx. Alright? Alright, so I hope you get it. No? So let's check using our calculator. No? So we have mode 1. So we have the integral of square root of 1 plus x cubed. One plus x cubed, limits from 0 to 2. 0 to 2. We get 3. So that is the exact answer. So this is the exact answer, 3.2413. No? So that's the exact answer, 3.2413. Okay? So if that's the exact answer, 3.2413, so for it to be near to 3 to the exact answer, for it to be near, so we can increase n, no, the value of n. So if we have n equals to 4, so if we have, let's say, n equals to 10, it goes nearer and nearer to the exact value, no, exact value of the integral, no. So this is expected because n is equals to 4 only. But if n equals to 100, for example, so we can that the approximation is very near to the exact value. Okay. All right. So we proceed now. So calculate the integral of x squared dx by the trapezoidal rule using 5 intervals. No? Solution: a equals to x sub 0 equals to 0. B is equals to x sub n equals to 10. For 5 intervals, n is 5. Okay? So if we have 5 intervals, that means n is 5. No? So we have the function f of x equals x squared, f of x sub I equals to f sub I equals to x sub I squared. No. So we replace x by x sub I. No. So this is the formula for h. So we have x sub 5 minus x sub 0 over 5. We get 2. So therefore, if h is 2, so this will be the constructed table. Okay. So we start with, so we have 0 squared 0, 2 squared 4, 4 squared 16, and so forth. And the integral using trapezoidal rule, we have, so for n equals to 5, we have the answer of 340. Okay, we can check our answer. This can be integrated easily. Integral of x squared dx from 0 to 10, that is 1/3 x cubed. The integral is 1/3 x cubed using power formula, limits from 0 to 10. So that's 1/3 10 cubed minus 0 cubed. So what is 10 cubed over 3? 1000 over 3. 333.33. Okay? Okay, so let's see. So we have 1000 over 3. Okay, 333.33. It's, so this is the approximated value now. This is the exact value, 333.33. We can check our answer. So the integral of, x squared dx from 0 to 10. No? So we get 1000 over 3, that is 333.3333, and so forth. Okay, so that's it. No? But if we increase the value of n, so because in our example n is 5, if we increase that by, let's say, 50, 100, okay, our approximated answer will be near to the exact answer. Okay, it will be very near to the exact answer. Alright, so that's it. So number 3, at t equals to 0, a body of unit mass in kilogram, initially at rest at the origin, begins to move along the x-axis under the influence of a force F is equals to 1 over square root of 1 plus t cubed, such that F is in Newton and t is in second. Find the velocity of the body at intervals of 0.2 seconds from t equals to 0 to t equals to 2 seconds, applying trapezoidal rule. Alright, let's analyze. So we have this figure. So we have a force is applied to a body of unit mass. Okay, that is 1 kilogram. It is initially at rest at the origin. Begins to move along the x-axis under the influence of a force with this equation. So such that F is in Newton and t is in seconds. Find the velocity of the body at intervals of 0.2 seconds from t equals to 0 to t equals 2 seconds. Okay? At intervals of 0.2 seconds, we are going to determine the velocity of the body. So in example, for example, at time 0, what is the velocity? At time 0.2 seconds, what's the velocity of the body? Then you add another 0.2 seconds, 0.4 seconds, we get 0.4 seconds. What is the velocity of the body at 0.4 seconds? And so forth. So we have t sub 0 to t sub 10 now. No? So that is, so this is time 0, then 0.2 seconds, plus 0.2, 0.4, plus 0.2, 0.6, plus 0.2, 0.8, plus 0.2, 1, plus 0.2, 1.2, plus 0.2, 1.4, plus 0.2, 1.6, plus 0.2, 1.8, plus 0.2, we get 2. So n now is 10, sorry. N now is equals to 10. Okay? So applying Newton's second law of motion, F equals to ma, right? So the force is equals to the mass multiplied by the acceleration. Now, so this is a lesson in physics where the acceleration is equal to the derivative of the velocity with respect to time. Then the velocity can be obtained, okay, using integral calculus. No? So this can be, we can rewrite this as a dt equals dv. Okay. So then we integrate a dt. Okay. So we integrate a dt. So d will be removed, and acceleration is f over n. Okay. So therefore v equals to integral of f over m dt. So such that v is in meter per second. So for mass equals to 1 kilogram, so this will be the equation. So F is 1 over square root of 1 plus t cubed. Dividing it by 1 kilogram, we get this. So V equals integral of 1 over square root of 1 plus t cubed dt. So in this case, A of t is equals to 1 over square root of 1 plus t cubed, wherein the acceleration is expressed in meter per second squared. Okay? So we know that the force is in Newton, mass is in kilogram. Newton per kilogram is meter per second squared. Now this acceleration, so we can replace t by t sub I. So we have a sub I equals to 1 over square root of 1 plus t sub I cubed. Then the velocity is, we know this formula that is derived. So it was derived in the previous slide. No. So this is, so we can rewrite v, no? We can replace it by v of t, no? V as a function of t. So this t can be replaced by t sub I, okay? So therefore, the limits will be t sub 0 to t sub I, no? So when we replace t by t sub I, the limits will be from t sub 0 to t sub I. So this is v sub I now equals to the integral of 1 over square root of 1 plus t cubed dt, limits from t sub 0 to t sub I, will now be approximated applying the trapezoidal rule. No? Applying the trapezoidal rule. So this is now h multiplied by 1/2. So this is f sub 0, f sub 1 in our formula. So because we use a, no? In this example, we will replace f by a. So we have now 1 half a sub 0 plus a sub 1 plus a sub 2 and so forth. Okay? So we have this. So age is 0.2. Okay, as computed, as stated in the problem. Okay, as stated in the problem, at intervals of 0.2 seconds. Okay, then we start from 0 until we reach 10. Okay, so we start from 0 until we reach 2 seconds. So interval of zero point 0.2 seconds. We have the interval of 0.2 seconds. So therefore age is equals to 0.2 seconds. So 0.2 second. A sub I, okay, at time 0. So at time 0, so 1 over square root of 1 plus 0 cube. So we use this formula, no? Okay, we replace t sub I by 0. So 1 over square root of 1 plus 0 cube. So we get 1. We replace, okay, so then v sub I, so this t sub 0 is 0. Okay, so 0 at time 0. So at time 0, what is our velocity? At time 0, our velocity is 0, no? So at time 0, so v sub 0 for I equals to 0. So if this is t sub 0, from t sub 0 to t sub 0, that is 0, no? Because there's no velocity yet, no? So from t sub 0 to t sub 0. Okay. So that is 0, no? And then at time 1 second, we have, sorry, at time 0.2 second. So this is t sub 1. I is 1, no? This is t sub 1, this is t sub 0. So this is 0 and this is 0.2 seconds. Okay? This is 0 and that is 0.2 seconds. Okay? So to get 0.9960, okay, we replace t sub I here by 0.2 because this is now t sub 1. T sub 1 is 0.2 seconds. So this is 0.2. Okay? So 0.2 seconds. Then cube. Okay? And then, so then we'll get 0.9960. Okay? And then, how did we arrive at 0.1996? So applying the formula. So from t sub 0 to t sub 1, so you'll have a sub 0 and a sub 1, right? So what's the formula here? This is t sub 0 and this is t sub 1. So age 1 half a sub 0. So what is now n? N now is 1 here, right? N is 1. So if n is 1, so, or should I say if I is 1, so that is 1 half a sub 1. I is 1. Until we reach 1 half a sub 1. Okay? That is h 1 half a sub 0 plus a sub 1. Okay? That is only a single trapezoid. No? This is only a single trapezoid. 1 half h a sub 0 plus a sub 1. Then we will get an answer of what? So h is 0.2 multiplied by 1 half. Then a sub 0 is 1. No, that is 1. A sub 1 is 0.9960. Okay. So let us simplify what is our answer using calculator. So using calculator we have, so 0.2 times 1 half times 1 plus 0.9960. So we get 0.1996. So we get this value. So that is 0.1996. Okay. Alright, so next, how about, so this is t sub 2. So this is t sub 2. So we now replace this by 0. So we now replace, so this is t sub 2, which is 0.4 seconds. Okay. Alright. So this one we have, so we replace t sub I by 0.4. So this is t sub 2. So a of t sub 2, that is that is a sub 2 equals to 1 over square root of 1 plus t sub 2 cube. But t sub 2 is 0.4, no? So that is 0.4. So that is 1 over, so we have 1 plus 0.4 cube. No. So let's see. 1 over square root of 1 plus 0.4 cube. So I'm using my calculator now. So 0.9695. So there we have that. We have this. Okay. Then for the velocity, okay. So we have v sub 2 for the velocity. V sub 2 approximately equal to h, okay, 1 half. So we have a sub 0. We will stop at a sub 2. So plus a sub 1 So that is 2 minus 1, so that is a sub 1. Then we'll stop at a sub 2. So this is now 1 half a sub 2. Okay? Alright, so what is that? So that is h is 0.2. 1 half of a sub 0 is a sub 0 is 1. A sub 1 is 0.9960 plus 1 half of a sub 2 is 0.9695. So 0.9615. So 1 half of 0.961595. There. So we have our answer of what? So we get 0.39615 or 0.3962. 0.3962. So we get this. Okay? And the pattern continues. No? So I hope you get it. So our final answer will be at time equals to 0, v is equals to 0. No? So there will be no velocity at time equals to 0. So it is at rest. The body is at rest. As stated in the problem, at t equals to 0, a body of unit mass in kilogram initially at rest at the origin. Therefore, at time equals to 0, v equals to 0. It's not yet moving. No. So that's why we have 0 here. Then at time 0.2 seconds, that is 0.1996 meter per second. That is our answer. Because in the problem, what is being asked is what? Find the velocity of the body at intervals of 0.2 seconds. From t equals to 0 to t equals to 2 seconds, applying trapezoidal rule. Okay. So in that case, we have 0.1996 meter per second. And the likes. So until we reach t equals to 2 seconds, we'll get an answer of v equals to 1.4014 meter per second. Okay? So that is our answer. Okay, I hope you get it. No? So you will answer an activity. So simulate the solution of the given problem using Excel such that when the lower limit and or higher limit of the integral is changed, a new correct value of such integral will be obtained. Okay, so in this example, n is equals to 12. Okay, so you will use n equals to 12. Okay, okay. So trapezoidal rule. So this is what you will do. So what I did here is I considered n is equals to 4. So in your lab activity, you will consider n equals to 12. Okay? So when I change the lower limit or the higher limit or both, I should get a correct answer. No, I should still get the correct answer. No? Of course, it has a limitation. Uh, the inside the square root, it cannot be negative, right? The value of x cannot be negative inside the square root. Okay? So, so simulate the solution of the given problem using Excel such that when the lower limit, so I will change when the lower limit, when the higher limit na lang, no? When the higher limit of the integral is changed, so ito 2, 0 to 2, 0 to 3, 0 to 4, 0 to 4.5, ganon, no? So, dapat tama pa rin ang sagot. Kasi, hindi ko pwedeng gawin na negative 5 yung 0. Dahil 1 plus square root, 1 plus negative 5 cube ay isang negative number. Square root ng isang negative number ay imaginary. So, wala siyang area nun, no? So, dapat positive. So, ang gawin na lang natin, so 0, yung ating lower limit, papalitan lang yung higher limit natin, no? Okay? I hope you get it, no? So, ito yung ating given. So, n is 4. So, gagawin natin n is 12. So, ito yung age, no? So, ito, ginawa ko n equals to 4. Sa inyo, gagawin nyo n equals to 12, no? Ayan. Tapos, ito yung sagot. Using trapezoidal rule, no? So, 3.283262, no? 3.283262. Okay? I hope you get it, no? So, ganun yung gagawin nyo, class, no? So, ito naman, dito 20 yung ginawa ko. N equals to 20. So, ito yung lumabas na sagot. 3.242976. Dito, 4. 3.283262. So, mas malapit to sa exact value ng sagot. Check ulit natin ano yung exact value. Okay? Ano yung exact value? Square root of, this is 2, that is 0, and then ito naman, square root of, ay, ano nangyari? So square root of 1 plus x cubed. Okay, from 0 to 2. So the exact value is 3.2413. Okay, n is equals to 22. 3.242976. Ito yung exact 3.2413. So, lumalapit habang yung n ay nag-i-increase yung value. Dito kasi, n ay 4. Malayo sa 3.2413, no? Malayo. Pero pagka yung n, in-increase ko yung value, lumalapit sa exact value. Kaya siya, kaya yun. Kaya yan yung topic natin. Approximation of an actual function value for the area, no? Okay? I hope you get it, no? So that's all. So, good day everyone.